today's topic? Graph transformations and some basic graphs. So linear graphs, quadratic, cubic. Also quartic is on syllabus. That's equations that have an x to the 4 in them. We'll also look at reciprocals, some questions involving intersections, translations, stretches of graphs, and reflections as well. All right. I'll see if there are any more students that want to come in. And then I'll get started. All right, guess I'll just get started then. Okay, so simple shapes that we need to know. Small powers of x. So equations of the form y equals mx plus c. It's a linear equation. Quadratic, ax squared plus bx plus c. We've covered both of those in earlier seminars. Cubic has this general form with a not equal to 0. Let's take a look at a couple of the general cubic shapes. So with quadratic, there are effectively two shapes, right? Positive, negative. Cubic, there's more x terms, and this causes there to be more curvature, possibly, and more possibilities for different shapes. So let's start with the simplest cubic, that is y equals x cubed. Gives us this kind of shape. Okay, and at the origin, that is a stationary point and a point of inflection. The way that we can prove that is to consider the first derivative, which is 3x squared, has a root at 0, and then the second derivative is 6x, which also has a root at 0. And then the last thing we have to do is compare the gradients on both sides. And we see that it's increasing before and after, which means that this is a point at which the curvature inflects. We also have a similar shape for odd powers of x. So if I have y equals 2 to the 2n plus 1, where n is a positive integer, I'll make that a 2n minus 1. No, 2n plus 1, yeah. Then we have the same kind of shape. The higher n goes, the more exaggerated the curvature. Notice that we get a negative branch down here because when we have a negative number and multiply it by itself an odd number of times, the result winds up being negative. Okay, some other interesting shapes we can get with this. This is a cubic which is increasing everywhere, but it's not strictly increasing because it is stationary at the origin. We can come up with cubics that are strictly increasing everywhere. That is to say their derivatives are always strictly greater than 0. Such a cubic might look like this. And an example of this would be something like x cubed plus x. We can prove that this graph is strictly increasing everywhere by considering its first derivative, which is 3x squared plus 1. And this is always greater than or equal to 1, which is greater than 0 for all values of x. In other words, its derivative is always greater than 0, exactly what we want. The graph is always sloping up. Another way we can view this is to sketch the graph of the derivative, which will look like this, strictly above the x-axis. Cubics also allow us to have more curvature. So quadratics have exactly one turning point. No points of inflections on a quadratic, but with cubics, we can have 2 turning points. Something like this. So similar equation to above, but instead of a plus x, I'll have a minus x. And now notice that always the derivative of a cubic is a quadratic, so we can always find the number of stationary points by taking the discriminant of the derivative, because the derivative is quadratic, so we can always look at its discriminant. Here, the b squared minus 4ac is just 0 minus 4 times 3 times minus 1. It's greater than 0. And so there are two distinct turning points, right? One here and one here. Another way to think about turning points is that they are boundaries between the function being increasing and decreasing. So if I was to draw vertical lines through these turning points, splits it up into increasing, then decreasing between the roots, and then increasing past this root again. We also have the negative shapes of all of these. All the ones that I've considered so far have a positive leading coefficient. That is to say, the coefficient of x cubed is positive. If it's negative, we have basically all of these, but reflected in one of the axes, say the y-axis. Right? So instead of being increasing, it'll be decreasing. It'll start up here, finish down here. This will be the negative shape. Okay, another way that we can view cubics instead of their expanded form is to look at their factorized form. The factorized form is nice because it immediately tells us the roots. For example, if we come across a cubic, and it can be written as x times x minus 2, x plus 1, we immediately can get a pretty good idea of what the graph looks like. Actually, I'll throw in a minus in front. We still have a good idea of what the graph looks like. First thing we do is look at the leading coefficient. That's the coefficient of x cubed. It's a negative x cubed. So it's always it's going to look something like this, with possibly some curvature in the middle. We also know it has 3 roots. So a root at 0, -1, and 2. And sort of putting the pieces together, we can see that it's going to have 2 turning points as well. Right? One here, because it has to turn around after it goes through this root to go back up and hit this root. And then likewise on the way down here as well. So this is what the shape of the curve looks like, and we can fill in all of the roots. Yeah, and also notice that the y-intercept is 0 because every term is multiplied by an x. So overall, there is no constant term, hence the y-intercept is 0. Right, next on the syllabus are quartic graphs. We need to be able to sketch quartic graphs. So quartic derives from 4. It's an equation of this form. Here, E is just some real number, not to be confused with the exponential constant. All right, I will grab some, I have a convenient picture with a lot of different quartic shapes. I'll quickly find that. Yeah, here it is. Okay, here are some fundamental quartic shapes. So we can see that there are, in the first two, we get even more curvature. Right? We have actually the maximum number of possible turning points, which is 3. And the reason that's the maximum possible number of turning points is that the derivative of f is a cubic. And a cubic can have at most 3 roots. In general, if we have a polynomial, which is with the form x to the power of n plus some other terms and then a constant term at the end, it will have at most n roots. Because when we factorize this, there are at most n linear factors in that factorization, each factor corresponding to a root by the factor theorem, sort of the same way we solve quadratics by taking x squared minus 4, splitting it up into linear factors, and then now we know the roots, 2 and -2. Okay, other shapes that we can get some with points of inflection, like this one here. We can also get quartics that are sort of more exaggerated quadratic shapes. So we see that this is really sort of flatter at the bottom than a quadratic would be. And you can think of this graph here as just x to the 4, but translated to this turning point down here. So let's suppose that the coordinates of this point are a, b. We can use graph transformations to get to this, and I'll talk about more about this in a moment. X to the power of 4 is a graph that looks kind of like this, with the minimum point at 0, passes through 0. And we want the minimum point instead to be at AB. So how do we do that? We want to move the graph A units to the right and then B units down. So to do that, we do x minus a to the 4. This x minus a corresponds to moving the graph A units to the right, or it may also say A units in the positive x direction, which just means to the right. And then we need to add b. Notice here that b is a negative number, so we're adding a negative number. That just means moving the graph down by b units. And that'll take us to this. Okay, let's look at a question involving quartics. Oh, and also we have all of the negative versions of these as well. So the negative versions of all of these quartic shapes will be just the same, but reflected in the x-axis. And that's when we have, again, a leading negative coefficient of x to the 4. Okay, so here's an example of something like a graph identification question. In sort of a real exam question, this will probably be part of a bigger question. So we'll look at something like that later. Let's suppose I have a quartic that looks like this, and I know that this coordinate here is -2, and this one here is 3. So this function f, given f is a quartic, find the equation of f. Or I'll phrase it as find all possible equations of f. Okay, so we have to think about, what do we know? Well, we know its roots. We know all of their roots, -2 and 3. Now, what's special about these roots is that they are repeated roots. In other words, they touch the x-axis and then go back the other way. They don't just sort of cleanly pass through. And what this means in the algebra is that this gives us a squared factor in the factorization. So instead of just having x plus 2 as a factor, we know that x plus 2 squared is a factor. Same thing for the 3. And with that, we fully factorize the quartic. We've got 2 quadratic factors, which must multiply to give a quartic. Now, there's one bit missing here, which is that we don't know that the leading coefficient is equal to 1. So we have to write fx equals a times all this. So this a, what this a will effectively do is scale the graph up and down. And we'll look at that again with graph transformations. One thing we do know about a, given the way that the graph looks, is that it must be positive. If it were negative, we'd have the whole thing flipped upside down. Another sort of side question we could have with this, if it's a calculus-based question, they could ask you to find the coordinates of this minimum point. We'll look at that kind of thing at a later date. Another thing might be find the y-intercept in terms of a. To do this, we just plug in x equals 0. Which is 36a. Okay. Right, let's look at graph transformations. There are sort of 4 main graph transformations. 2 of them are sort of moving the graph around, up, down, left, right. The other 2 are stretching, so stretching in the x direction and in the y direction. And the other 2 that I'll look at are reflections. And I'll relate that to symmetry of certain functions. Right, so let's get the nice ones out of the way. These are the translations. For this, we will be working with a function y equals f of x. And then for particular examples, I like to use trigonometric functions because each of these graph transformations has a very distinct effect on these trig functions. So I'm going to pick sine. For reflections, we'll probably need something else, but for the first four, we'll be good. Okay, so suppose I take f of x and I transform it to f of x plus k. That is, I just take my entire function expression and put a plus k at the end. This is just translating up by k units. Think of this as also shifting the y-intercept. A relation to calculus is that when I take this and differentiate it, well, the constant differentiates into nothing, so I just get f prime of x, which is the same as if I differentiated f. So they differentiate into the same thing, which is to be expected because k is just shifting the graph up and down. It's not actually changing the derivative at any x value. We would expect all of the other transformations to do that, but not shifting up and down. So this is k units, and I'll write this as in the positive x direction. Oh, by the way, if you have any questions throughout, just feel free to throw them in the chat, and I'll answer them whenever. Okay, other translation. Cool. F of x minus k. The reason we have a minus k here is sort of one way to see it is suppose we have the graph of x squared. We are taking our input x, what I like to think of it as the input, and we're replacing that with x minus k. So this will go to x minus k all squared. And this, sort of relating to the earlier stuff, has a repeated root at k. So we can see that the graph of x squared, which has a repeated root at 0, has been shifted k units to the right. Oh, wait, that's only one's meant to say positive y direction. There we go. This one's x direction. All right, so up, down, left, right. Okay, next are the stretches. These are a bit more confusing because there's sort of an extra idea of a scale factor of a stretch. And there's a reciprocal in one of these as well. So let's suppose I take fx and I move it to k times fx. So I take my entire function expression and multiply it by k. This is a stretch in the y direction. When we say it has scale factor k, which I'm going to abbreviate as SF. Okay, best seen with something like sine. If I take k equal to 2, then this simply pulls the graph out, sort of up and down, doubling its amplitude. Now, if my scale factor of a k is between 0 and 1, this will be a compression rather than a stretch. For example, if I have something like this, a plausible value of k would be something like a half. So in this case, it's actually gone inwards. But we sort of keep the language consistent when talking about these stretches, and we always refer to them as stretches, sort of when writing on paper rather than compressions. So you could view this green transformation as a compression by scale factor 2, but it's a stretch by scale factor 1/2. And then the equations of these respectively would be 2 sine x and half sine x, doubling and halving the amplitude respectively. Okay, and this is the confusing one. We get a stretch, this time it's in the x direction, but this one is scale factor 1/k. And sort of to convince yourself of this, it's probably easier to think of this in terms of a compression. So if I have my graph of sine x again, and I overlay the graph of sine 2x, I'm doubling the frequency, so the roots appear twice as often. And you can see that this is easier to think of as a compression. Yep. It's an algebraic method of showing why it's 1 over k. Let me think about that. It's close because the scale factor can be thought of as it's just simply defined as 1 over k. Okay, another way I like to think about these is we're taking the x-axis and replacing it with a kx-axis. And then we apply the function. Let's think about a way of answering that. Okay, this is probably how I'd answer it, and I'm not sure it's satisfactory, but we're taking the x-axis and replacing it with a kx-axis. So suppose I scroll up and we look at ways of interpreting this in terms of transformations of the axes. So for this transformation here, we're taking the x-axis and replacing it with a x minus k-axis, and this will have the inverse effect on the graph. So the axis will move k units to the left. This sort of thinking about it relatively, the graph will move k units to the right relative to the axes. So there's that kind of inversion there. This is the additive inverse. For this, it will be a multiplicative inverse. So we're replacing the axes with the x-axis with a kx-axis. So it'll cause the stretch to be 1 over k rather than k. This will be easier to do with an animation. What I'm thinking of is taking the XY plane, overlaying a square grid. And then when I replace the x-axis with a kx-axis, the vertical lines will become way closer together. If I then take those vertical lines and stretch them back out to where they should be originally, this time bringing the graph along with it, the graph will stretch out accordingly. So let's say I take my k equal to 4, and this becomes way more compact. And then I take the vertical lines and stretch them back out so we have squares rather than rectangles. Taking the graph with it, it'll stretch the graph out like this. And the factor by which I'm stretching it, I'm taking these sort of unit rectangles now in the lattice, which have height 1 and length 1 over k, and I'm stretching that 1 over k length back to a k. So this whole process corresponds to a stretch with scale factor k, which is why we get the graph to be dilated outwards. And then for the opposite effect, if we have scale factor 1 over k, then it will be compressing inwards. That's the only other way I can think about explaining this, but I'm not sure about like a pure algebraic approach. Okay, what was I? So, yep, that gives us stretches with scale factor 1 over k. I prefer to think of it as a compression with scale factor k. And clearly k cannot be equal to 0 because otherwise we get division by 0. Okay, often in questions, we'll need to be composing these together. So if we look at the translations, it doesn't matter. Suppose we just have two translations, one up and then one to the right. Doesn't matter what order in which we do those. It's like we're at a block in town and we can go right and then up, or we can go up and then right. Doesn't matter. We end up in the same destination. Same thing for the stretches. We can do a stretch in one direction and then in the other direction. The order, just with stretches, does not matter. Another way to see this is that the translations affect outside the bracket and inside the bracket, which means that they do not interact with each other. Same thing for the stretches. This one manipulates the outside, this one manipulates the inside, so they don't interact with each other. The ones that do interact with each other, which is where the order of function composition matters, is these two, because they both deal with stuff outside the brackets, and then the other two, which deal with stuff inside the brackets. We have a sort of a parallel here, which is that this is going up and down, so in the y direction. This stretch is in the y direction, and then the other two are in the x direction. Basic example of where the order matters. Suppose I have x, and I map it to 2x, and then I raise it up by 1. If I do it the other way around, the stretch in this part of the transformation doubles the effect of the earlier translation, so it's not equal to each other. Yeah. Common questions just involve sketching some graph transformation. So you're given a function f. You may not even be given the algebraic function. You may be given the sketch of it. And then you may be asked to sketch, okay, sketch the graph of 3y equals fx or something. And then it's easier to then rearrange this to get y as the subject. And then you look at it, find the appropriate graph transformation, and then sketch it. Let's do a simple example. This is the graph of x cubed minus x. I'll take this to be my f. And let's suppose I want to get the graph of a third fx. So the third being outside means that this is a stretch in the y direction, but because it's a third, which is between 0 and 1, this will end up being a compression effectively. So we can think about what points of this sketch, or rather what points of the graph will be invariant under this transformation. That'll be everything on the x-axis. It's going to stay exactly where it is. And then we think about where did the other points go. So this maximum, the y value is literally being 1/3. So it's going to return to, it's going to go to about a third of its height. Same thing here. It's going to go about there. And then we can see that the curvature, sort of joining the dots together, is going to be a lot shallower going forward. The algebraic view on this is that if we're looking for intersections, this is just solving this equation, which rearranges to fx equals 0, i.e. the roots. So this equation could be thought of as saying, what are the intersections between the two, or what parts of the graph are invariant, in other words, do not change under this operation. We can do the other stretch as well. So f of 1/3 x. Go ahead and take every instance of x and replace it with 1/3, which gives 1/27 x cubed minus a third x. I'll do this one in green. So this time we're looking at a stretch in the x direction with scale factor 3, which is the reciprocal of 1/3. Okay, and we can look at how the equations compare. So third fx, we're doing a third multiplied by the entire expression. So there is a slight difference between these. This is 1/27x cubed. This is 1/3x cubed. Okay. One way to see how these differ is to factorize them and look at their roots where they've ended up. And we can sort of get a good idea of where they've ended up because this is a stretch in the x direction. Just algebraically, we have 1/27x, x cubed minus 9x. So this x squared, yes, should be 9. So now the roots, instead of being at 0 or 1, are at 3 and minus 3, as expected, right? It's been stretched out by a scale factor of 3. And the origin has stayed where it is. So all of the points that are invariant under this are going to be all the points that are on the y-axis. Because we're just looking at functions, there's only going to be one such point. In this case, is at the origin. But when we're looking at graph transformations of things like circles, say moving circles around, or stretching circles, if you're doing that, stretching and squeezing them into ellipses, there will be more than one point which is unaffected. For example, if I take a circle here and I apply this transformation, come on, pen, please work, then it will end up like this. A bit wider, obviously, but these 2 points will stay where they are because they are on the y-axis. Okay. They also mention graphs of reciprocals on here. So the graphs of y equals k over x and k over x squared. I'll probably look at those in a moment, but there are 2 more symmetries that I need to do, or rather 2 more transformations, which are the symmetries or reflections. I think I'm going to just do the ones that are on syllabus, which are reflections in 2 axes. But you may also be interested in other kinds of reflections, for example, reflections in the line y equals x and reflections in the line y equals minus x. This one's particularly important because if you have a function and you reflect it in the line y equals x, and you have a function, once you do that, that is the inverse function. And the way to see this graphically is that reflection in the line y equals x, what it does, if I picture the axes as 2 pointed arrows, I am taking each arrow and mapping it onto the other arrow. So the x-axis flips onto the y-axis and the y-axis flips onto the x-axis, and they're both still pointing in the right direction. So what this does in the algebra is it replaces every occurrence of y with x and every occurrence of x with y, which is precisely what we do when we try to find the inverse, right? If I have y equals a to the x, if I replace this to get x equals a to the y, then solve that. It's just definition of the logarithm. Okay, good. I've shown that the exponential and logarithms are inverse, and you can check that they are reflections of each other in the line y over x. Okay, back to the symmetries that are on syllabus. If I have the graph of y equals f of x and I put a negative sign in front of it, what this is doing is this is taking every y coordinate and replacing it with its negative. You can think of this as taking the y-axis, this big pointed arrow, and flipping it upside down. So if I have a point that's, say, up here, it gets reflected down here. If I have a point here, it gets reflected down here. If I have a point down here, it gets reflected up here. You get the idea. The x-axis is the mirror line. So this transformation corresponds to reflection in the x-axis. Okay, and then we have the other one, which is doing the negative of the input rather than the negative of the output. This is taking every x value and replacing it with its negative. Similar reasoning to before gives us that this is a reflection in the y-axis. So, couple of examples. Let's take that graph from earlier, x cubed minus x. We'll show something interesting, which is that no matter what axis we reflect it in, it's the same result. So let's take this to be g. G of minus x is minus x brackets cubed minus brackets minus x. This gives minus x cubed plus x. And then minus g of x is, well, minus x cubed plus x. So they're the same. Now let's think about the significance of this. And before we do that, I'm going to consider what happens when we combine these graph transformations. So let's do f of x. We'll send it to minus f of x. And then we will do the subtraction of the inside. So minus f of minus x. Okay, so I'm reflecting it in the x-axis and then in the y-axis. Now, the overall effect of this you can gauge by taking some rectangular object, preferably a book, flipping it vertically, and then flipping it horizontally, and then seeing what the net result is. And the net result is a rotation of 180 degrees about the origin. And I recommend doing it yourself with something, maybe like a credit card will work. And what's cool is that the order of these transformations does not matter. Okay, so you can do these reflections either way around. It's the same net result. Okay, so back to this g of x function, this x cubed minus x. We have that g of minus x is the same as minus g of x. To make it more similar to what we have, I'll take the x and substitute it for minus x. So g of minus minus x, which is x, equals minus g of minus x. Same thing, just done a variable substitution. So we can see that if we have the function g and we apply both transformations, that is rotate it 180 degrees about the origin, nothing changes. It's just equal to what it was. So this means the graph has rotational symmetry of 180 about the origin. And we scroll up and we can sort of see plausibly, yeah, it does. And then if you have a function where it's equal to its negative, then it has symmetry in the x-axis. If you have a function where f of x equals f of minus x, then it has symmetry in the y-axis. A couple of interesting identities related to this. Sine x equals minus sine of minus x. That is to say, sine has this rotational symmetry property. You can convince yourself of that from the graph. We also have cos x equals cos minus x. That's symmetry in the y-axis. And then using trig rules, you can divide these two together to get that tan also has this rotational symmetry. Right. So we've shown here that the order of reflection does not matter if we're just looking at reflections. If we're just looking at stretches, the order of stretches does not matter. If we're just looking at translations, the order of translations does not matter. The time where we have to be careful about the ordering of these different kinds of transformations is when we're affecting the outside or the inside more than once. All right, from what I can see, that covers the syllabus. I'll just go through and see if there are any minor points. If there are any particular areas you want me to cover, I mean, we've got 20 minutes. Happy to cover anything, to be honest, even if it's off topic. Still matter related, but yeah. Okay, in the meantime, I suppose I'll talk about the circle equation in terms of mechanics, or the common questions with static, rigid bodies. Static equilibrium. So common question types will be, you might have a particular particle, and then you have different forces acting on that, and you'll have to construct some kind of triangle, not necessarily right-angled. So you do this by treating the forces as vectors and putting them together head to tail. Another kind of common question is just stuff on slopes. You have some kind of preventative force that's added on to stop it from moving, to keep it in equilibrium. Maybe you can throw a pulley in there as well. And maybe say, for what value of the weight that's down here would you need so that you exceed the limiting friction, something like that. I mean, mechanics questions could be a combination of all sorts of things. There's also moments as well. So I think, yeah, you could have something like moments as well, where an object is, suppose, either fixed pulley there or just a fixed pin, something like that. There's friction, and then here. Then there'll be some center of mass, another resultant force. And then this question can involve taking moments, which you should do about this point here because it eliminates the most variables. Just leaves this one, assuming you know the weight. And then also resolving forces horizontally and vertically. I'll just look through the textbook, see if there are any major areas that I've missed. Yes, I mean, the key thing involving the ones I've listed are that, so if you're in static equilibrium, you're not only having a zero resultant force, but you're also at rest. So because you're at rest, we can consider ideas about limiting friction as well. So sort of being on the point of moving. I'll see if you can find an interesting question related to that. Okay. Circle equation and completing the squares, just viewing the circle equation as a translation of the circle centered at the origin, translating it A units in the x direction and then B units in the y direction. Completing the square can also be viewed as taking the quadratic x squared and then moving it so its minimum point is at AB. This is the minimum point, which you can see when you complete the square. That's what that was about. Right. Okay, let's consider a slope setup with a pulley on top. Light inextensible, so we have the same tension on both sides. Just a block here. $30 degrees. And we'll have something here, say 5 kilos, 2 kilos. And we're going to assume that this system is in rest. So I've got to give names to these objects. A, B, system at rest. This question is not about a system at rest. That's not what I wanted. All right, yeah, I'll do one with a ladder. Okay, so a ladder rests on a wall. And this ladder is at rest, but it's in limiting equilibrium with an angle of 60 to the ground. We will fix a load onto the ladder, call it C at this point here. This distance is A and this distance is 2A, so it's a third of the way up the ladder. And it will have a mass of 2m, so this is 2 mg newtons weight. Right, what else do we know? So the ladder itself will have mass. Assuming that the ladder is uniform, we can suppose that this is halfway along, so mg newtons right in the middle. But that is an assumption that we have to make. So given that the system is in rest, we can consider some forces. So there will be a resultant force R. There must be friction along the floor, we'll call that F, or otherwise there's nothing to oppose the contact force that is on the vertical wall on the ladder, which we will call P. Okay, and then we can assume that the vertical wall is smooth, otherwise it'll get too complicated. Okay, and then because there's a problem about limiting equilibrium, we want to find the coefficient of friction. Okay, so first things first, resolve forces. Well, first thing first is actually to draw the diagram. Now we resolve forces. When in doubt, resolve forces. The only two horizontal are F and P. We know they're equal to each other. And then resolving, say, downwards, we know that the resultant force R is equal to the sum of the two weights, which is 3 mg. Next thing we can do is take moments, and we want to take moments about a point which eliminates the most variables. A good choice seems to be right at the bottom of the ladder. We get rid of R and F because they're at a distance of 0 from the pivots. Another hint that we might need moments here is simply the fact that we're given distances, right? So this weight is a distance from A, from the bottom of the ladder, sort of going along the slant height. So moments at ground. And here we need to look at the components of the weight. So we resolve these components parallel and perpendicular to the ladder. So a component of these weights are going through the ladder, which are pointless. Those don't affect the moments. The ones that do affect the moment are the ones that are perpendicular. So for example, this 2 mg splits into a 2 mg cos 60. Likewise with the mg. All right. And then we add those up. So distance times and this is mg cos 60 that's acting at the midpoint. So that's 3/2A. Yeah, good. And then we look at the forces that go the other way. R and F are discounted, and we're left with P. Won't highlight. Hold on, technical difficulties. Okay, I've made a mistake here. We shouldn't be doing moments at the ground because we want to find F over R. We should be doing it at the wall. So I'll fix that. Okay, this will give us an equation involving F and R. We also know that R equals 3 mg. So this will give us an equation that relates together mg and mu. And these mg's should cancel, giving us mu by itself. Right. So this expression should simplify to 2.75 mg. And then we have a cos 60, which is √3/2. So this will be 3√3 over 2 sine 60. No, the sine 60 is √3/2. So it's a 3√3/2f. I'm also going to divide, should be an a there. I'm going to divide by a throughout. Okay. And then because we're in limiting equilibrium, we can say that f is mu r. And then from this, we know that r equals 3 mg. So this is 3 mu mg. Okay, substituting this in gives and then we have our expression for r in terms of mg, 3 mg. And now the mg's all cancel, which gives us mu in terms of just numbers. And if I put that into my calculator, it's about 0.225, the three significant figures. Unitless quantity because this is force over resultant force, and they're both in newtons, so the newtons units cancel out. It's just a coefficient. Okay, so that's one example of a question that you might get. I made a mistake along the way, which was to take moments at the ground. It was not a good idea because I was not interested in finding P. I'm interested in finding an equation that relates F and R because it's to do with limiting friction. The only instance in which I want to resolve at the ground is if I can solve for a variable that I'm actually interested in, like P. But if I do that, I get P in terms of M and G. By resolving horizontally, that does give me F in terms of M and G. But then I don't have the equation that relates together F and R, which I really need. So I have to take moments at the wall. All right, that brings us to time. On next week's schedule is straight line graphs. And that probably won't take very long. So if you've got any other questions you want me to do, just bring them in, just post like a screenshot or something in the chat and I'll just do it. All right, I guess I'll end the class there. Thanks for coming and have a good rest of your week.